All right, so we're going to carry on with the next section, which is input and output, intro to programming in Python. So we're going to be covering various sections in this lesson. I'm just getting a pointer here. We're going to look at standard input and output, standard drawings, fractal drawings, animation, and standard audio. Comparing this to the actual notes, which is actually section 1.5 on the book site. The only one that is not actually covered is fractal drawings. It could be maybe in the Q&A exercises, but it's not actually covered. So this will be something new that's in the slides that covers it. But everything else is covered in the Princeton course. Check online, which is for free. So basic building blocks for programming. We've covered quite a bit. Now we're on to the section of graphics, sound and image, and input I/O. We have already done some I/O or inputs and outputs with text. Now we're going to expand that as well. So inputs and outputs, the goal is to write Python programs and interact with the outside world by input and output devices. We have many typical devices: a keyboard, trackpad, storage, network, camera, microphone. And outputs is display, storage, network, printer, and speakers, for example. Our approach is to define input and output abstractions. We use operating system functionality to connect our Python programs to actual devices. So what is abstraction? Abstraction plays an essential role in understanding computation. And abstraction is something that exists only as an idea. So example, printing is the idea of a program producing text as an output, right? We use the term print we use all the time in programming, but essentially printing is the idea, remember we're abstracting this concept of a program, computer program, producing text as an output. Good abstractions simplify our view of the world by unifying diverse real-world artifacts. This lecture, abstractions for delivering input to or receiving output from our programs. And there are various examples of outputs here. Quick review. So in the terminal, an abstraction for providing input and output to a program. This is an example. This looks like Java code. I can see it's running Java over here. And it calls, well, this is code that seems to draw cards from this program, random cards. Decker suites, we've done this already in the previous lessons. This Java code looks very similar to Python code, bar a few exceptions. But it just draws random cards from a deck. And then they have a similar program. I'm not sure where this is not from Princeton course. I'm not sure where they are running this. Maybe they developed their own one. But you have an input from command line, which is draw cards, and the output is the various cards that you get. As an example, I ran it with Java. Input outputs abstraction so far. So it's useful to have a mental model of what a Python program does. So a Python program has some command line arguments, like the name of a person or numbers. Python program is a black box, does something, and the output is some standard output stream, something to the screen maybe. So command line input, an abstraction for providing arguments or strings to a program. So most times our arguments were input as strings from terminal because it's input via keyboard. So it's important to understand how we need to take that and maybe convert that or cast it into float or keep it as a string. So basic properties. Strings you type after the program name are available as argv, argv1, runtime, as we've seen already. Arguments are available when the program begins execution. If you need to call system conversion methods to convert the string to other types. So I've done this before, seen it before to create that. to create that. Which we actually call casting when you convert to different types. So here's a little program that they're running over here, which looks pretty straightforward. Its purpose is just to create a random variable and multiply it by n, the value that you're giving. Main function, get an input value, whatever it is, for example, 6, get a random value, and then t is that value times n, and right line that. So I think this code looks pretty straightforward. There's nothing too complex about it. I think this is just showing or demonstrating inputs and outputs. Review standard output, infinity, an abstraction describing something having a limit. Okay, standard output stream, an abstraction for a finite output sequence. Okay, so basic properties. Strings from standard write line are added at the end of the standard output stream. Standard output stream is sent to terminal application by default. So let's have a look. Here we have another program, and its purpose is to write a whole bunch of random numbers to the screen. So this is code that randomsec is actually part of code here, code base. I've tried to copy most of it already. So here I have, this is from the Python course. They have just defined a function which you can also do. They're also using, maybe let's try and do what they did. So create a function here, definitely not really necessary to do this, but let's try and mimic as much as possible what they've done. So, okay, that's fine. argv for I and range of n is fine. And this is standard std random.uniform. Evolves in function uniform. And then they have the standard entry point for the program. Again, for such a small program, this is really not necessary, but just try and copy what they've done. Okay. So what does it do? You have gets the input 4, and that'll create you 4 random values. Let's run that. This program is called Python random sequence. Say 4. And I spelled this wrong. It says it's complaining about standard random. Maybe did it mean uniform int? Maybe that was a problem. Let's have a look. Low high. Okay, so I'm not sure why this program. Let's maybe stick to what you had before. Random. I mean, this again, this just to illustrate the same thing. So let's maybe stick to using this one rather, and run it, and we get the values we're expecting. I think I should just update it like this. There we go. Now I get the random numbers. So you can pause the video and try it yourself. Improved input-output abstraction. Add an infinite input stream. So here was this a quick example of if you have like I think this looks like a million. There's like no limit on amount of output, right? It'll just give you a whole bunch of numbers. How we can improve our input-output functionality? Well, we can have an input-output abstraction. Prove this by having another input, a standard input stream. So it might have commanded arguments, but you might have an input stream as well. Again, it will still give you some standard output stream. So standard inputs. So infinity, again, is an abstraction describing something having a limit. Standard input stream, an abstraction for an infinite input sequence. So the advantages of a commanded input can provide new arguments while the program is executing. So useful. A limit on the amount of data we can input to a program. All right. Conversion to primitive types is explicitly handled. Stay tuned what that means. So let's have a look. So standard I/O does a lot more than just standard write line. Again, developed for this course, but broadly useful. Implements abstractions invented in Unix, available for download at book site. So it has other built-in features, which is very useful. It has is empty function, read int, read float, read bool, read string, and read all strings. So it does much more than just writing to the terminal. It also has these we're all aware of, write line. There's also a new one called writef. Writef allows you to writef allows you to have certain formatted output. If you have certain amount of decimals, you can specify that. If you want a certain data type, you can also specify that. So this gives you more flexibility with the output, how it should look. These are similar to the print function. Why not just use print? Well, we provide a consistent set of simple I abstractions in one place. We can make output independent of system language and locale. Okay, fair enough. Writef. So this is this function over here. They didn't actually complete this train of thought. I thought they would have, because I'm just trying to see how this links to the website Princeton course, but I guess I'll mention it shortly. Would actually have an input program that would be input into this one. But let's see what else to say in the notes. Sure, it's coming. So writef, which is part of standard I/O, allows you to format the string. You can do set conversion types if you convert it to float, string, bool, whatever you want. You can also specify the amount of decimal points. So it's an anatomy of a formatted print statement. So you can have for int, the code you need to use or specify if you only want an int is D, for float it's F and E, for string it's F. So we'll look at a few examples. So some sample strings you want to use 14%, 14D would mean use 14 characters printed on the right. It is a minus and it prints on the left with spaces on the right. An example here, 14.2f shows numbers after dot shows the decimal places. So 14 is the total amount of characters including the spaces. This one is 14s if string is less than number of created spaces within the remainder. So these are the outputs that you can expect. And the examples here, 14D minus 14D, and the various other outputs. Input, output, warm-up, interactive input. Prompt user to type inputs and send input stream, mix input stream with output stream. Okay, so again, this code looks pretty straightforward. It asks the user type the first integer, and they get an integer. I think read int we've never gotten before. We use sysarg, so maybe let's type this out. Create a new file. Create a new file here called, this is called add int. That's it. Add 2 to the file. Standard out, so input standard IO, import sys, find function. Again, for such small programs, you don't need to do this, but this is a couple of what they've done. Type first integer. Okay, store that. Now we're using a new function we have not used before. We're reading an int. We're not using sysarg anymore. We're specifying this built-in function called readInt, standard IO readInt. And it says standard IO. Let's copy this. So I have to type less, type second integer. And then this will be, we're going to store that into a y. So we're going to store two integers, x and y. And then we're going to do summation. Summation equals x plus y. And then you can go to print the result, I'm guessing. So red line. The sum is plus string summation. And let's create the entry point for the program. All right, let's try to run this code, see what happens. So it's going to be Python add 2. Add 2. There we go. So the type was integer. So let's say 1 and 2, and boom, we get 3. Let's add a space over here. Make it a bit neater. 2 and 3 gives a 5. There we go. Simple application of inputs and outputs. Input application, average the numbers on the standard input stream. So this code is from the Princeton notes. So we can use this. So read a stream of the numbers and compute the average is the goal. And this is the code that does it. No limit on the size of the input stream. Input and output can be interleaved. How do I specify the end of a stream? Control D or Control Z. Control C for Mac. So let's see, I do have this program over here. It looks quite similar. Total is 0, n is 0, while not std is empty. So the key part of this that is new is we're checking inputs while we do not get an empty float. So if we're getting numbers, it will continue to make this true or not empty. It's expecting values. And then it reads in a float, works as a total and increments a count, and you work out the average. So I'm not going to rewrite it in this way. The code is pretty much identical, just without the function built in. You can run it, you can say Python average, and then it's like, as many values you want, it will work out the average. If I don't input anything, say enter, then it won't do anything. I have to probably press Control C or Control Z. It did not, or Control D. I'm supposed to do Control D. Terminal. Have that one, so 5. Control D. There we go. Okay, Control D worked. Average is 40. So summary, prototypical application of standard output and standard input. We have one that generates a stream of numbers and another that computes an average stream of numbers. So how do we actually put these two together? This would be interesting to do that because one works out as many like integers you want. The other one works out based on infinite number of integers, give me the average. So both streams are finite, no limit in the size. So do I always have it to type in my input data and print my output? No, I don't. It can be automated. No, keep data and results in files on a computer or use piping to connect programs. This is what we're going to do. We're going to pipe the two programs, which is effectively the one goes into the other. Redirection. So we're going to, okay, before we do piping, they mentioned piping, but we're not going to cover it yet. Follow the notes. So, yeah, the Princeton notes has a bit of a better structured and how they explain things. But in the case, the jumping back force a little bit, redirection. So how do we store data? So the question was, do I always have to type in input data and print an output? So you don't always have to print out your data. You don't always have to print out the output. You can actually store it in a file. And you don't always have to input data. You can also input it as a file. So redirection, the greater than and less than symbol allows you to redirect data. Redirect data to a file, redirect data from a file. So the example here is, okay, then I do piping. Okay, so let's say I have, where's my random sec? Yeah, so let's say I run my file, Python, random sec, random sequence, and have 10 numbers. Okay, I get 10 numbers. Now, instead of outputting those 10 numbers to the terminal, I can actually save it to a file. And I'm going to save it to a file called data.txt, as it's shown in the notes. So we do that with the greater than symbol. It just redirects it to a file that has not been created yet. If you want to append to an existing file, it would be double greater than sign, but if it doesn't exist, or create a new file each time, single one. So now it's saved it to data.txt. Let's see if it's created. Yes, it has. There it is. And there's a result. Very nice and neat. Now we can redirect from file to send input. So now we can take this data and input it into our average function. It's a Python average. And we can use a less than symbol, which means the data must be used as an input into average of pi. And we get the result of 0.517. Very cool. This is a nice application. Nice, nice way to understand how the input files, output files work. This is problem, still slight problem, still limited by maximum file size, obviously, which is true. So random sequence, we have a random sequence that creates a file, and that file goes to an average. So you can actually bypass this whole file thing completely and just make the output of random sequence the input to average. And this is effectively what this little image shows. We can do this with piping. So there's no room for a huge file on my computer. Now what? Well, no problem, just use piping. Connect standard output of one program to standard input of another. Use it with the pipe symbol, which is usually the key, maybe next to your enter on your keyboard, piping symbol. So we can say Python random sec. Create 10 values. I'm not going to create 10 a million. Just I'm going to show you an example. So make like 20. I'm going to pipe that output into, let me just make it bigger, into Python average. I get my input. It worked out the 20 random values and input that into Python average. Very nice, very neat, and very useful to understand how this works. Critical point, no limit within programs on the amount of data that it can handle. If it is the job of the system to collect data, send an output, and provide send an input. So it's a very nice little example. Redirecting send output to toast a printer. So you can do this as well, little simple example, hello world to dev toaster. It's a little playful example, I guess. Streaming algorithm. So early computing. So amount of available memory was much smaller than the amount of data to be processed back in the day. But dramatic increases happened every year, and redirection and piping enabled programs to handle much more data than computers could store. So with modern computing, the amount of available memory is much smaller than the amount of data to be processed. Dramatic increases happen every year. Streaming algorithms enable our programs to handle much more data than our computers can actually store. Listen, avoid limits within your program whenever possible. Standard drawings. now we're moving on to drawings. So let's have a look. So further improvements to our IO abstraction. So add the ability to create a drawing. Okay, so we use the Princeton's book site library. We have a standard input stream for part of the program. We have command arguments. Now we have some drawing as the output. We use a standard law library developed for this course. Very useful to do it, and you see the standard output as well. So what are some of the functions of standard library? You can draw a line, a point, draw text, draw circle, square, polygon, picture, set pen radius, color, scale. Very importantly, you need to show how that works. And it's important to understand why you need show, because it's like a buffering mechanism. You can draw a circle, but it only shows it once, it only displays it to the screen once you call this show function. And this allows for better outputs of images. Otherwise, it might be delays and slow down your program if every time you run a function like circle or pinpoint that you create an image. So we use this to show everything at the end. This is better explained in my other video where I cover the section in more in depth. Again, they're only giving a few slideshows here. Here are examples of creating circles and squares and different shapes, different programs to do it. Yes, again, this is all from the Princeton notes. Examples of how to do it. All right, so the first thing I'm going to do is a Hello World for standard draw, which is drawing a triangle. Now, I do have this over here, the triangle. So there's a bit of a problem with the environment I'm using, because it is a virtual environment, it's not local on the machine. So effectively, the code is the same. I'm not doing a function like they did. I don't really, it's not really necessary. They set the pen radius to make it thicker. Okay, I can add that if I want. But they are effectively drawing a triangle. So I'm not showing this to a little window. I'm saving it, but effectively everything else is the same in the code. Importing the libraries I need, standard draw and math, and create my triangle. And then instead of showing this as a pop-up window, I'm going to save it as a file. So let's run it, see what happens. Python triangle, pi. And see if it was created. And there's my triangle. One small difference here is that they also change the set pin radius. So we can make it 0.01, maybe like make it like 0.1, make it a bit thicker. Run it again, see what happens. The triangle. Yeah, it's super, super thick. All right, so that's maybe a bit overkill. Let's make it smaller, 0.01, I think, also better. Confuse. There you go. I have a little bit thick, but it's fine. There you go. So that's how the code works. Line by line, what it does is first works out, it draws the first line, again 0.0, specifies, well, this is the, very importantly to understand, 0, is the bottom left of your screen, the bottom left of your window. So I'm saying draw a position, and let me actually specify this as well. So standard draw, what it does, it says from x0, y0, x1, y1. So the x0 is y0 is 0.00, as specified there. And my next point is x1, y1, which is 1, and 0, which is over here. So this will draw that line. And then the second line has an angle. So in that sense, we need to specify that with the t value, which is worked out with square root of 3 divided by 2, and then also drawing the point in the middle. And then they also did standard draw text to draw the text in the middle. That's a bit different to what I did, but you can try that out yourself. Pause the video and try it yourself. And then this is what I try to repeat. Stop and try repeat what I've done or what you see on the screen. This is the output. So exercise to draw a square using lines. Again, this would follow the same process. Again, bottom left 0 and 0 and 1 0. So this is very similar step. Start here, draw your bottom line, then draw top right, top line, bottom line. So let me see if I can quickly do this. Okay, I'll copy this and see how long it's going to take me. Square the pi. Because it should be quite self-explanatory. Point, so 0, 0, 1, 0, that's fine. And then my other point is 0, 1, and a 1, 1, the top line. And then my two upright lines. It's also going to be 0, 0. And then it's going to be 0, 1. My other right line is going to be 1, 0, 1, 0, and 1, 1. Yeah, I think that's it. See if I got that right. Python square. My square. There we go. I drew my square. Cool. So this is the code. Stop the video, try it yourself. But it's quite straightforward. And if you want to draw the point, I mean, you can try that yourself. Just draw the point like I did with the triangle. Well, exercise for you. Oh, there you go. Okay, all right, they did it for me. Okay, standard draw application data visualization. So now we have something a bit more intense where we want to draw a plot of the USA. Okay, so I also have this code as well. This is a function called plot filter. Let's have a look. Plot filter. There it is. The only thing they've done, again, is create a function. What it does is it reads X and Y scales from standard input and configures standard draw accordingly. Then it reads points from standard input while in the file and plot them to standard draw. So it takes points, sets a scale, so it fits, and then while not empty, it will keep on drawing a point, X and Y, until all the values have been created. So we have this data. We're going to redirect it of all the points from USA. So here it is. This is all the data points, all X and Y 0 points to create this plot. So let's see how that looks. So Python plot filter pi, redirect that USA text. See what you get. And again, I'm saving it. I mean, you will have this as a see little dots, all created from based on the text. Very cool. So you will have a window popping up. I'm saving it as a file. Standard draw application plotting a function, plot y equals sin 4x plus sin x, 20x an interval, takes in samples regularly. Again, you can do this yourself, copy and paste the code. Again, this is quite straightforward. How do you plot functions? How do you create sine waves? you have to create two 1D arrays, X and Y, with a bit of math to work out the 4X. This is the first X is going to be your interval, which is 0 to pi, and then Y is your actual Y function. So this is 4X. There it is, 4X over there. Let me point again. So this is 4X over there. So over there, sine 4X plus sine 20X over there. And the interval is specified 0 to pi is specified with this 4 range over there. And yeah, that's how it's drawn. And this different lines are drawn in this way. Okay, fractal drawing. So this is not covered in the notes. So we can take an example. So to draw application of a random game, draw an equilateral triangle, label the vertices R, G, and B, and make R the current point. Pick a vertex at random, draw a point halfway between that vertex and the current point. So they give you the algorithm or methodology to do this. And this is the code. So let's do this because this is not in the notes. So let's try this out. Let's call it chaos. See what we get. I'm going to maybe copy the code from Triangle because I need to save the file. I cannot one pop up as a window. Okay, standard draw. I need to import standard random. stdrandom. I'm not sure why standard. The others. Let's try standard random. I'm not sure if they're using uniform again. Yeah, uniform didn't work from my side. I'm not sure if it's a problem with the library. And import math and import sys. Okay, got that. I'm not defining a function. That's not necessary. I have trials. Trials is int. Getting input from terminal arg v1 arg v1. I have c is math dot square root. I already have that. Having t, I can see. And then I have these two lists. Cx is 0.0, 1.0, and 0.5. Cy is 0.0, 0.0, and C. Was this defined in here, maybe in this vertex? I think this is what it's defining over there. Standard draw. Okay, so I'm not worried about the pen. X is 0.0, Y is 0.0. For loop for T in X range, 0 and 0 to trials. And that is R is int. Let's try standard random. Maybe it does work this time. If not, we'll just use other random. Uniform times 3. And X is X plus CXR, out of 2.0. Got that because it's similar to Y. Y is Y plus CR divided 2. And then we draw these points. Standard draw dot point X and Y. And standard, okay, now we're going to save it. Save this as chaos. All right. Okay. Cool. Let's see if this works. I'm not sure about standard random though, but let's see. So Python chaos, what they want 1,000, what 10,000. Let's make it smaller. Let's make it 100. Chaos of pi, make it 100. So it happens. X range is not defined. It didn't mean range. I think that's correct. Not sure I said X range here. It's a typo. Yeah, it's a typo. This code wouldn't actually work. This is X range is not correct. This is other, I think this is Java. Yeah, uniform int, maybe. Yeah, I'm getting this issue again here. What's this one? I don't think they ran this code. Um, yeah, I don't think they ran this code. Let's just do random, and random. I don't think they ran this code. This is another, yeah, I don't know. Let's try it now. Okay, let's see what you get with chaos. Oh, it does work. Okay, nice. Cool. But we have two little points. So let's add some more points. Let's make it 1,000. Nice. 10,000. Cool. Actually, surprised it worked. I didn't actually try it before. So cool. So the algorithm worked and it worked quite well. So, Sierpinski triangles in the wild. Um, examples of that, quite interesting. So, easy modification, color point coding to random vertex chosen using standard draw set pen color to change pen color. So, I can do that as well. You can specify this is the adaptation of the code. For R0, 1, or 2, you can change a different color. So I can try that in your own code. Pause the video and try it yourself. Iterated function systems. What happens when you change your rules, probabilities, and different probabilities, new x, new y? Ifs.py is a data-driven program that takes the coefficients from these carl.x. Again, this is examples. I didn't get code much here. We can try it yourself if you want. If you want to know how this works, you can let me know in the comments. Iterated function systems, another example of changing the rules. You can get something like this, or something that looks like a fern. It's interesting. Iterative function systems, simple iterative computations yield patterns that are remarkable, similar to those found in the natural world. So a fern, real plants, quite interesting. What does computation tell us about nature? What does nature tell us about computation? Interesting. There are formulas and algorithms that actually are related to them, I guess. Note you have seen many practical applications of integrated function systems in movies and games. So these, like plants and ferns, were probably not, drawn. They will probably use these kinds of iterative programs that will just naturally draw it in some way, form based on based on algorithm. So it'd be quite cool to actually try this out yourself. So I was actually quite um, interested in this actually. I want to see how this actually works. So I was actually able to generate this code. You can have a look at this here. Because it's actually, this is quite very interesting actually, how you can create like a fern based on a few lines of code. You can see these algorithms, the formulas coming from X, Y, and um, to generate the stem and the left leaflet and right leaflet. And these functions are pretty much based on what's this called above here. Was a term they used above here? Yeah, Sierpinski triangles. Yeah, this is actually very cool. That's why I actually wanted to try it myself. And there it is. Here's the code. You can stop the video, try it yourself to get these triangles. I'm sure it's probably online as well. But I thought this is very cool. Just try it myself. And I use like, this is 10,000 random values or trials, so I can try it out. Yeah, yeah. Cool. So that's that In terms of animation, to create animation with standard draw, to repeat the following, you clear the screen, move the object, draw the object, display, and pause. So I cannot unfortunately show this unless you create a movie, but this you should be able to, test yourself. The example I have is with a bouncing ball position, and with constant velocity. To move the ball, you update the position. If the ball hits a vertical wall, bounce it back, Vx to minus Vx. If the ball hits a horizontal wall, set Vy to minus Vy. Here's the game. You can take this code, copy it, try it yourself, and you should get the output. What they're doing to create this is changing this clears the background. How the animation works, let me explain it like that, is literally just these 3 lines of code is what's used to make the animation. It gets your position Rx, Ry, okay? Clears the current image, draws a little circle or the ball, and then shows it. And then it works out the new XY with this function, clears it, draws a new circle, and then shows it, and then repeats a step. So it looks like it is an animation. That's pretty much it. All right, next and final section is standard audio. What is this? This is a set of I/O abstractions for Python developed for this course, but broadly useful. Standard I/O, in-stream, outstream, standard draw, and standard audio. Available for downloads. Again, you can get this from Princeton course to test out writing audio. So what is sound? There's a quick crash course in sound. Sound is perception of vibration of molecules. A musical tone is a steady periodic sound. A pure tone is a sinusoidal waveform. Western musical scale as concert A is 440 Hertz with 12 notes, and various other examples of different notes. So digital audio, to represent a wave, sample at regular intervals and save the values in an array. With antibody arrays, so it should be simple to create these sine waves. So it's examples of, for example, samples per second, samples, and what the wave looks like. The more samples you have, the cleaner sine wave looks like. This is a CD standard with 44,000 samples per second. Bottom line, you can write programs to manipulate sound using arrays of float values. Now, the standard audio library is developed for the course, very useful. You can play sound wave on your computer's audio output, convert it to a format .wav format. I'm not sure if they can explain it, but WAV format is like a binary format. It's a lot easier to store it than actual floating point values. So the library has play file, play samples, fair sample, save, float, so a few functionalities to return. It enables to hear the results of your programs that manipulate sound. So here's a very simple example. This is in the notes on the website Princeton course. Hello World for Studio called Play That Note. I think I did. It's not here actually, but it is on the site. This just allows you to create the sine wave. This creates a sine wave for you over here. And then this function takes that array and then creates the sound for you on your speakers. So something cool you can try. Here's an example of Frere-Jacques exercise if you want. We can write down the notes. What they are. Yeah, here's the example that they showed above. How to do it. So try it out yourself and see what you get. We did a list of tones and duration from standard input to play a tune. To play the tune, this is how you can, play the tune based on the input file as well. So, different ways using this library. Yeah, that's it for this section. Hope you learned something. Until next time, goodbye.